6.6 is a very large section. It's on rational functions, which means that we'll have some polynomial being divided by another polynomial. So there's going to be a whole lot more going on than was happening with just a polynomial function. It's going to combine knowledge from a lot of our previous sections. And so I'm going to start simple and work to harder, which means that I'll just start with a transformed reciprocal function, so a transformed version of 1 over x. So I've given f of x here as 5 over 2x minus 1. So if you remember from the previous sections what 1 over x looks like, then the transformations that are taking place here are a horizontal shift right by 1/2, a horizontal stretch or squish by 2, and a vertical stretch by 5 in this particular problem. So if I graph it, what happens is that vertical asymptote gets moved to the right by 1/2, because we had a vertical asymptote at 0, right, when x is 0. Now it's at when x is 1/2, because we divide by 0 if 2x minus 1 equals 0 instead of x equaling 0. And likewise, we have a horizontal asymptote at y equals 0. That's the same as before. Because we didn't have any vertical shift to the problem, we just shift it over and then we make it a little bit stretched by the 2 and the 5. And so that's about the simplest case you can get. If we go a little bit harder and we say, what if we have a linear polynomial divided by another linear polynomial? Because that was a constant divided by a linear polynomial. So the next step would be incorporating a polynomial on top and on bottom. So now we have an x on top and an x on bottom, with f of x equaling 3x minus 1 over 2x plus 4. Now, a nice way to reduce this down to determine what your horizontal asymptote is to reduce it to a constant plus a transformed reciprocal. So then I'm looking for some way I can write 2x plus 4 inside of the 3x minus 1. So 3x minus 1 being written in terms of the denominator, so that I can reduce that to a constant and then just have some added term on the outside. So I'm saying that 3x minus 1 is equal to some constant a times our 2x plus 4 plus some other constant. And if I do that, I know that I can get a 3x, right? The x is a big deal here. I need to make sure my x's match. So for a times 2x to equal 3x, I need to multiply by 3/2. So that tells me that the a in that case would be 3/2, which reduces that down. So I have 3x minus 1 equals 3/2 times 2x plus 4, the whole quantity, plus some constant b that I still have to figure out. So 3x minus 1 equals 3x plus 6 if I distribute the 3/2, plus b. Subtract the 3x from both sides, getting me -1 is equal to 6 plus b. Subtract the 6 from both sides, and that tells me b is -7. So I can rewrite 3x minus 1 as 3/2 times 2x plus 4 minus 7. So then that tells me that I can take these parts, right, take the 2x plus 4 in the denominator, and I can split the numerator into 2 pieces because it's the numerator. Can't do that with the denominator. But then I have 3/2 times 2x plus 4 over 2x plus 4, which reduces to the 3/2 that we found, minus 7 over 2x plus 4. Okay, what this tells me is that now I see multiple things happening. I see that my vertical asymptote is of course shifted. That's the part that comes in here. And I also have a vertical shift of 3/2. That's the new piece to this puzzle. So the vertical asymptote happens when 2x plus 4 equals 0, because I'm still going to approach infinity if I divide by 0. So I just solve for what x is equal when 2x plus 4 equals 0. And I will find that when you subtract 4 and then divide by 2, you're left with x equals -2. So I have a vertical asymptote at x equals -2. The horizontal asymptote, as I mentioned, is the vertical shift. And so since it shifted up by 3/2, then there's a horizontal asymptote when y equals 3/2. Okay, so we have a vertical asymptote and a horizontal asymptote sorted out. Horizontal shift to the left by 2 is what that results in, and a vertical shift up by 3/2. Those operations, those transformations, are causing the vertical asymptote to move to a -2 and the horizontal asymptote to move up to a 3/2. What we are also seeing by the form that we have, the 3/2 minus 7 over 2x plus 4, is that there's horizontal stretch or squish by a factor of 2, and there's a vertical stretch by a factor of 7, but then there's a negative in front of that function, which means that it also will have reflection over our x-axis, okay? So this is a little bit tricky, but what's happening is I'm multiplying the function by a negative, so the whole thing flips, okay? Now, if I apply these transformations, we can see it in the graph. But there's one more thing that gets added to this particular function because we have a function of x in the numerator, the 3x minus 1 term in the original function, because we had 3x minus 1 over 2x plus 4. When 3x minus 1 equals 0, we will get an x-intercept. Because if the numerator is 0, we have 0 divided by something, and that just gets us 0, which means we have an x-intercept. So if you solve for when 3x minus 1 equals 0, you will find that there is an x-intercept at x equals 1/3. That's another piece of information that we can use when we're graphing this. So I have sketched in the graph, and you can see that if you recall, 1 over x looked an awful lot like this. I'm just going to sketch it in here, very rough, not very pretty, in purple. So you can see that what has happened here. We flipped it over the x-axis, we shifted it up by 3/2, and we shifted it to the left by 2, and then it's got a little bit of a stretch to it also from the 2 and the 7 that cause it to look a little bit different than just flipping it over and moving it. Okay? But I hope this helps you with the visual. There's a reason that I attached a Desmos lab to this section, and that's because it is the hardest section to visualize. So bear with me. An application of why on earth do we deal with these functions is the focusing distance of a camera lens. If you've ever worked with any kind of optics, or if you've worked with a camera, then you would be somewhat familiar with this relationship. If I have an object that I'm trying to take a picture of, then I have the distance between the lens and the photo, like the actual image that's produced, and then the focal length for the particular lens that I'm using. There's a relationship between these three things that's defined through 1 over x plus 1 over y equals 1 over f, where x is the distance of the actual thing you're taking a picture of. So your friend, how far are they from the lens? Y is the distance from the lens to the image that's produced. Say if you were dealing with a film camera, that would be the distance from the actual lens to the film where the image is being produced. And then the focal length is specific to the lens itself. So in your camera, you're going to have a focal length that corresponds appropriately to define an image on your film. Notice that if you try to take a picture of an object that is closer than the focal length for the particular lens, you're not going to get an image. It's just going to be blurry because it's just not made to do that. And I have a small drawing here to try and show you why that's the case. So this equation is only going to be valid for distances of an object that are greater than the focal distance of the lens itself. So if we need to figure out where an image is produced, let's start with an example of a 75 millimeter lens. So that means that f is equal to 75 millimeters. Now, that tells us that we can now define a relationship between the image distance and the object distance by solving for y. So I have 1 over x plus 1 over y is equal to 1 over 75, and then I need to solve for y. So I'm going to subtract that 1 over x from both sides, And then I have a reciprocal. I have 1 over y is equal to 1 over 75 minus 1 over x, and I can combine those with that dead smiley, x minus 75 over 75x, to get x minus 75 over 75x. Since this is a reciprocal function, 1 over y, I just flip the fractions on both sides of my equation, and that tells me that y is then equal to 75x over x minus 75, which we can sketch. And you can see that it's already sketched in here. I have a vertical asymptote when the denominator is equal to 0, so when x is equal to 75. I have a horizontal asymptote when y is equal to 75, actually, because that is effectively the bare minimum. It's not actually going to ever equal 75. That's why it's a horizontal asymptote. It's approaching it, but it never reaches it. So that's what this one is, right? Notice that I didn't sketch in a left side of the graph. There's no values on the left side of the vertical asymptote because no image is actually going to be produced if the object is not more than 75 millimeters away from the actual lens. If we use the same lens and we try to take a picture of a person that's 2 meters from the lens, that means that it's 2,000 millimeters. Since we were talking about the focal length in millimeters, we want to be consistent when we talk about the distance that the object, which in this case is a person, is from the lens. So what is the image distance in this case? So I came up with an equation to determine the image distance based on the object distance. So we just substitute the object distance into our equation. Y is equal to 75 times 2,000 over 2,000 minus 75, which reduces to about 77.92 millimeters, right? Notice this is a little bit more than the focal length. It can't go below the focal length. And then this is my picture, which if you've ever done physics or studied any kind of optics, you would be somewhat familiar with it. I'm betting that you are not, but this would be the location of your object. And then if we trace the light rays that travel, and we assume they're perpendicular to the lens, where this is your lens, if we track those light rays to the lens then causes them to diffract a little bit, and so they close in to the focus, to your focal length, and the focal point corresponds with where those rays all cross. And then they continue on, and that's why you usually end up with a flipped over image, because the top tracks to the bottom, right? This, if I go along, goes to the bottom, and the bottom tracks to the top. And so that's why our images in those pictures are often flipped over, just based off of how the light travels through the lens and where the focal length is. Because your image has to be past the focal length, you end up with that flip. So this, of course, is your image. On this side, that would be where the film is collecting that picture. And then I drew in here, right, if I just put these lines in to denote where things are, x is the distance between the object and the lens, y is the distance between the lens and the image, and then your focal length is hidden in here. It's that length between the lens and the focal point for the particular lens. Notice that as your x value increases, y is going to get closer and closer and closer to f, so the image size is also going to decrease. Where I am right now is a much bigger than if my image wound up, say, here in this little picture. Then the size of my image would get smaller and smaller and smaller. And then last thing that I mentioned was that if x is less than your focal length, your image can't focus. So if this object moves in too close, then the lens is no longer going to be able to capture the light rays and focus them on a focal point. It's going to be unable to actually focus.